If you're happy, I can give a very brief summary of what I intended to talk about, and it's really to tell you how exciting it is to think about the next a couple of decades in science, which I think will be largely defined by quantum physics and what we've learned about quantum physics through quantum information, going into the more and more complex systems. So I wanted to, that's why I mentioned going into life, into chemistry and biology, and then trying to understand the whole universe. Now, what I think will be crucial in this case is how we understand quantum mechanics. And really, my focus for this, it's a very simple, really, lecture, very basic introduction, is my feeling how we should be thinking about quantum mechanics. And it seems to me that if we think about it this way, we are going to get um, more readily in many ways to the either next theory, um, by performing some experiments that are telling us really something genuinely new, or we will simply develop a better understanding of things that we don't understand very well already in complex systems. So my first slide is really this a very simple story that comes, I think, from Buddhism, where you have two monks. I call them apprentice monks in training, who are basically looking at the flag that's waving and in the wind. And one of them says, "Look how beautifully the flag is waving." And the other apprentice monk says, "I think you are wrong about this. The flag is not waving; it's the wind that's blowing, and the flag just follows the motion of the wind." And the master walks by and accidentally overhears this dialogue. And he approaches them and says, "Both of you are wrong. It's neither the flag nor the wind that are moving, but it's actually your mind that's moving." And I like this. I like this story because it presents basically three different ways, very broadly, very crudely speaking, three different ways in which we can understand um, the world in general. But of course, it applies to quantum mechanics, and we can probably think about three different ways in which we think about the foundations of quantum mechanics in this way. So let me go very briefly through this, and then I will get into the bit that I think is relevant for us and how I think we should think about it, and how this will get us into asking really fruitful questions that we can start to address experimentally as well. And that's what's exciting to me, that we are on the verge of being able to test some of these. So cubism is quantum Bayesianism. It's one interpretation of quantum mechanics, which would kind of, in this story I told you, it would correspond to the mind this way. It's all in the mind. That's what the master is supporting. So according to quantum Bayesian approach, quantum states are just like probability distributions. They're like classical probability distributions. They are telling us about the lack of knowledge that we have. It's all about that. It's nothing to do with the system itself. It's really all to do with our perception of the system. So it's a bit like tossing a coin. Before I observe the outcome of tossing a coin, I don't know whether it's going to be heads or tails, but so I'm assigning some probability distribution to that, if you like, and after I toss the coin, I know the outcome. However, we know that there is a problem with this, and it's simply called the interference. And I'm not going to take you through this basically, but every quantum system we tested so far, be it a massless particle like a photon in this case, or more complicated atoms. Certainly, we've done it with nuclei, components of nuclei. We've done it with charged particles, larger molecules, and all of that. We know that all of these phenomena have one thing in common, and it's called the superposition principle. So all objects, according to quantum mechanics, can be in many different states at the same time. So here I have this famous photon going through a beam splitter and ending up on two sides of the output of the beam splitter simultaneously. And we know this because if we recombine these two paths, like on my picture B, we know that ultimately these two will cancel out when they are going to one of the detectors, in this case detector 2, they will amplify when they go to the other detector. So we know that even though we are talking about a single particle, it could be an atom, it could be a molecule, we know that somehow it must have, along this journey, gone down both of these paths at the same time. And that's this famous concept of a superposition. So it's very difficult for a cubist, for a quantum Bayesian person to maintain the view that these are like classical probabilities. We know that that's not the case. The second, broadly speaking, the second view on quantum mechanics is that actually it's incomplete in some sense. There are some kind of hidden variables which we haven't discovered. So that would be corresponding to, in my story, to the flag itself holds the key to the behavior. It's just that we haven't understood the flag well enough. Now, again, in quantum mechanics, we know that this is very difficult to maintain because of at least a large, broad class of hidden variables ruled out. There are no numbers, real numbers that we can specify, which would really tell us better whether the photon, for instance, would come out of the beam splitter one way or the other. We've ruled these things out, and we've ruled them out through something that we call Bell's inequalities, which is really a test of entanglement, and I will get to that. So we know, for instance, that if we have two particles which are perfectly aligned in terms of how they spin, so this is the famous example with, let's say, two electrons or two photons, and if one is spinning one way, the other one is spinning the opposite way, and vice versa. We know that whichever way we measure one of these electrons, in whatever direction we choose in space, the other electron will exactly spin in that direction, but in the opposite sense, in counterclockwise instead of clockwise, let's say. And this tells us that there is no way that these values could have been pre-assigned. There are no real numbers, in other words. That's why people say that the choice that Bell's inequalities gave us about reality is that we should either forget about Einstein's locality, forget about relativity, which means we should admit that something travels faster than light, or we should forget classical real number-based reality. And I think my inclination is, of course, to go with the second choice. I think relativity is really well confirmed. It's a theory that makes perfect logical sense. And it's something that should not be abandoned very lightly, which leaves us, of course, with the second choice that the underlying elements of reality are not real numbers. That's really where quantum information comes in. That's what I want to tell you about. The underlying elements of reality are these very complicated objects, which Dirac called Q numbers, quantum numbers. So these are numbers. They can be represented in many ways. Usually we do them with matrices in physics, but it doesn't matter at all. The key property of these numbers is that the order in which you manipulate them, you measure them, matters. They don't commute. If you measure one Q number and then another Q number, it's not the same as if you reverse this. And this is the origin of the famous Heisenberg uncertainty principle, but actually it's the origin of anything else you care to choose in quantum physics. It's also behind the entanglement and behind how we understand quantum measurements. And that's really what I want to tell you about. But this slide just says even this second interpretation that there is something we're missing, it's very hard to maintain because we have quite a lot of evidence that there are no local hidden variables. Now, the last interpretation, this possibly has been the dominant one, although maybe in my field, more and more people are starting to think like what I'm now going to present. And I don't think Copenhagen, even though it was dominant in the early days and people say it won over all other views, I don't think it's appropriate. It's simply not good enough for the following reasons I'm saying here. Copenhagen would correspond to the wind doing things, again, very crudely speaking, in the metaphor, in the quantum Buddhist Zen story, if you like. So this would say something like, well, when the quantum system may be doing all sorts of weird things, being in a superposition and things like that. However, when it gets in touch with the classical apparatus, then one of the outcomes will materialize, and that's the key thing for quantum measurements. So the reason why I don't think why Copenhagen is the right way to think about quantum mechanics is because Copenhagen thinks about the world in a dichotomic way, and I don't think that's right to do. We don't need to do that at all, actually. So Copenhagen says there is the quantum world. We don't know where it stops, but certainly microscopic objects all behave in a quantum way. And then there is the large classical world that, let's say, we inhabit. And this classical world, when it gets in touch to make a measurement with the quantum world, creates some kind of reality. So I don't like this simply um, um, epistemologically. I don't like it, first of all, philosophically, because I don't want the world to be made up of two different kinds of entities. I want the same to be this. I want everything to be made up of the same objects. And that's what I want to tell you about these Q numbers. It's really the quantum information at the core of everything. And we should think of everything in the universe being made up of quantum bits. So the problem for Copenhagen, again, is really that it seems to suggest that measurements are something very special. It's something that brings about reality from these quantum superpositions that are not real. That's sometimes what people say. And they're not real in the sense that they can be described with real numbers, as I said, but they're real in the sense that they can be described with these quantum numbers. Q numbers exist. They exist like anything else we think of. That's how we should think of it in physics. So the fact that measurements somehow have a special status and they're not just any other interaction is also something that a person like me doesn't like very much. I don't think that's the correct view. And so this really summarizes this, that you really need some kind of external classical context in order to talk like a Copenhagen supporter. And to me, it seems that this would be a little bit inconsistent. How would I even do physics if half of physics was quantum and the other half was classical? In fact, you can show that all sorts of other notions fail if you go down that road. It's very difficult to maintain any conservation goals. Energy conservation is immediately out of the window. It can only be true statistically, but not in every instant, and things like that. There are all sorts of inconsistencies with this, and in fact, it can be tested whether the world is like this or not, and that's exactly what I'm excited about. That I think the next few decades will do exactly that. They will take quantum mechanics from the microscopic domain that we tested it and go into the more complex chemistry, biology, and even beyond that, the whole universe. So we should be testing these hypotheses whether the whole universe is quantum mechanical. And what does that really mean? How would one test it? And if we think it would fail, where would that fail? So here is my favorite view. What, again, I'm using the quantum Zen metaphor, if you like, that everything is really a quantum. A Q is here for quantum. Again, everything is a quantum wave. So the way to explain that picture is that the flag, the wind, the minds of everyone, everything in the universe is actually a bunch of quantum mechanical waves. So it's very important, not classical waves. You can't explain this with water waves and things like that. They have to be genuine quantum waves. And very briefly, if you're not familiar with this logic, and I will go into it a little bit more now, what that means is that the amplitude of the wave, the height of the wave that changes with time, that's how we characterize waves, is not a number. Classically, it's a number. But in quantum waves, this itself becomes a quantum, a Q number. And so that means it's not, you cannot characterize certain amplitudes of a wave simultaneously. You can talk about one property of the wave or another property, but you can't measure them. You cannot specify them at the same time. The same way that you cannot specify position and momentum of a particle in quantum mechanics at the same time. So of course, we know when it comes to electrodynamics, this means that you cannot specify all the components of the electric and the magnetic field. Classically, they are numbers. You can give them at every point in space and every instant in time. But quantum mechanically, the better you know the electric field, if you like, the less you know the magnetic. They're genuine quantum numbers. If you first measure the electric and then the magnetic field, you will get a different result to if you reverse your actions. And this is conclusively been established really in quantum optics that these are Q numbers. You have to think of electromagnetism as quantum waves. And now I'm making the claim that everything in the universe, all objects, material or non-material, are really just a collection of different quantum waves. And that's the best representation because it's it's not giving us any dichotomy. There are no two kinds of objects. There's only one kind of object in the world, and everything is made up of these. These are our atoms, if you like, in some sense, but they're really more like atoms of information, which behave in an unusual way than atoms of the ancient Greeks. And the question is really how does the reality that we perceive at our level, how does it emerge out of these quantum waves? Um, and um, um, and I want to tell you a little bit about it. That's a beautiful story. That's something that we do understand, but like I said, it's something that ought to be tested in more and more different scenarios. So this summarizes what I said about quantum waves. And the last point I'm making on this slide is that if you're thinking about any other effect in quantum mechanics, uncertainty principle, superposition principle, and ultimately the stuff I'll be talking about, quantum entanglement. Remember, that's something that Schrodinger said was the characteristic trait of quantum mechanics. They're all consequences, really, of these Q numbers. And so that's the picture that I prefer because somehow it's there's no duality here. There's no wave particle duality, which is what I want to show you now. You don't need to. That's been resolved in a way if you think of everything as a quantum wave. So this was this question in the early days of quantum mechanics. If you claim that small particles behave like waves, and this is a picture from one of the early experiments where an alpha particle, this is a helium nucleus. It has two protons and two neutrons. It's radioactively, so a larger nucleus decays radioactively, emits these particles, and then they're detected in what's known as a cloud chamber. So you have lots of molecules in this chamber. And when the alpha particle goes and hits one of the molecules, it excites the molecule. This molecule attracts other molecules around and it creates water vapor, which is like a small cloud. That's why it's called the cloud chamber. So you know exactly where the alpha particle is going because each time it hits a molecule, it generates a small cloud. And each of these straight lines is like a track. It's a sequence of clouds. It's actually discrete. You can see if you look at it a little bit more carefully, you can see that it's a sequence of dots, and each of these dots is an excited molecule. These cloud chambers resulted in a number of Nobel prizes about 100 years ago or so, but it's actually something you can make in your kitchen these days in about 5 minutes and do this kind of test yourself. I think if you look at it on YouTube, you can do that. But the question for these people, and I think the question that's still discussed, and I'm claiming that we don't need to discuss it anymore. We understood this. There's no problem there. The question is, how come if this is a wave, if this alpha particle is a wave, why does it go in straight lines? Why does it behave like a particle? Why doesn't it look like this? Why does the experiment look like a bunch of particles that are emitted and not like a nice continuous wave? This, of course, is a classical wave, but that's the key. That it doesn't look like this because it's a quantum, not a classical wave. And the explanation emerged out of a bunch of people who should get the credit for this. Heisenberg was one of the first to explain this. Then Darwin. This is a guy called Charles Darwin, a physicist, Charles Darwin, an English physicist who was the grandson of the Charles Darwin, of the biology. So not the same Darwin, but the same family. Neville Mott. In fact, lots of these things are known as Mott scattering. And ultimately, Schrödinger was really the person who nailed it. So if anyone is to be credited for this quantum wave picture of the universe, it's Schrödinger. So how did they explain it? Well, the explanation that they gave is that the alpha particle really, when it's emitted, goes in all directions equally. It really is like a wave, completely isotropic, spherical. It's the same in all directions. However, what leads to a classically looking trajectory is simply a sequence of interactions with the underlying cloud. But we shouldn't just be thinking of one of these trajectories as existing. We should think of all of them existing at the same time. And when we observe this, we just simply go into one of these branches, if you like, of quantum mechanics. But all the other branches, if you accept that everything is a Q wave, still exist simultaneously. So you see that this gives you a much wider reality, and it can be tested. That's also what I want to talk about at some point briefly. So Heisenberg had this very beautiful way of using Q numbers, and I don't want to bore you too much with this, where he said you should think of the particle starting as a wave, and then as it hits the first molecule, it localizes position in that place. And then as it continues, it broadens again until it hits the next molecule. So even though it looks like a straight line to us, what it really is, because we are looking at it at a higher level, which is coarse grained. But if you look at it at the refined level, at the very short distances, you can still actually see that there is a wave-like spreading of the particle. Then it gets localized by a collision. Then it spreads again, gets localized, spreads again. So very much how you would collimate a laser beam. You know, if the beam is emitted from a laser, starts to spread, then you put a slit, you narrow it down, then it continues to spread after the slit, then you put another slit and a sequence of slits. The mathematical explanation of how a particle behaves and how a wave behaves is in this case identical. The only difference, like I said, the big difference is that these are always quantum waves. They are waves whose amplitudes cannot be specified at the same time. They obey Heisenberg's uncertainty principle. So this view is something that's ultimately credited to Everett. But like I said, there is a long history. In fact, I think Schrödinger gave a set of lectures before it, maybe a year or two before. It's just that they were never recorded, and I think they were never published at the time. They were recorded and published posthumously. You can read them now. Where actually Schrödinger says more or less what I'm summarizing here. That measurement, all there is to measurements is simply not anything special, anything different from any other quantum dynamics. And it's basically the creation of entanglement between two quantum systems. We can call one of these systems an observer and the other one the system under investigation, but it's completely irrelevant which one is which. They're completely equal. They're all made up of Q numbers. That's the beauty here. So the distinction between the observer and the observed vanishes. And that's my claim here. That's, I think, where lots of research is going wrong these days, because people are looking for some kind of classicality ultimately that simply doesn't exist there. They're looking for some special agents, observers, objects that are capable of collapsing quantum things. But no such thing exists if you take quantum mechanics seriously and apply it to everything. That's the beautiful thing about it. It's not just an interpretation. You can actually test these things. And that's what I think will be happening more and more as our technologies advance. So the final thing, and Schrödinger was very strong on this point, he said, if you take this view that everything is a continuous wave, but a quantum wave, then there are no collapses. The collapse of the wave function is a wrong concept. That's not how this should be um, talked about. You can maybe talk about some effective collapse in your own branch, but it doesn't mean that the rest of it collapses. It's also an incoherent view. So Schrödinger said, I like this because there are no collapses, no quantum jumps, no discontinuities, no spooky action. Everything is nice and local. The Q numbers behave exactly as Einstein would have liked to have seen. So basically, if you change Q numbers in one place, this cannot affect any other Q numbers anywhere else in the universe. Nothing else changes. It's completely local, but local not at the level of numbers, as Bell tells us, but at the level of quantum numbers. That's the key. Once you accept that, everything falls into place, and there are no problems with relativity at all. Schrödinger made a very strong statement. He said, if I knew that we'd be talking about quantum jumps in quantum mechanics, I would have become a plumber instead of a physicist. So basically that's how disgusted, if you like, he was by various collapsed Copenhagen ideas, and I think he was right. So this was in the early 50s, by the way, just to give you the time frame. 1925, as we know, next year is 100 years of the anniversary of Heisenberg's first matrix mechanics paper. And it took about another 25 years before this view crystallized. And it's interesting, like I said, now I think it's gaining dominance, and it's gaining dominance because our technologies are becoming more and more advanced that we can actually test all of these things. Okay, so there was a slide there, set of slides just to reinforce this idea that everything can be made nice and local. I don't want to bore you with that. I'm just making a statement. If you have questions, I can go back and tell you a bit more. Now, the interesting thing here is that this is all consistent with the fact that we at the macroscopic level see classical behavior, meaning that objects are well localized. They're sitting in one place, not in two places at the same time, things like that. And the beautiful thing is that classicality itself is a consequence of quantum entanglement, of this view that everything is really a Q number. So in physics, that's another mistake we frequently make also when we teach. We start with classical equations of motion. We start with classical Hamiltonian, if you like, and then we create somehow a quantum Hamiltonian after. But that's not what nature does. Nature is quantum mechanical. And then in some very special limit, macroscopic limit, where things are completely decoherent, they are very entangled, you get some kind of classical reality that emerges. But it's a special case of quantum mechanics. So to make this statement extremely strong, Newton's laws of classical mechanics are a consequence of quantum entanglement. Newton would not be correct if the universe wasn't quantum mechanical. That's how strong it is. That's basically what I'm advocating. So classical physics owes it to quantum mechanics. And that makes sense because quantum mechanics is an exponentially larger theory. It contains quantum physics as a special unit. The way quantum computer scientists understands this is actually very simple. It says it says if you make a lot of measurements, so if the first qubit, this is like a control NOT gate, is measured by a second qubit, which in turn is measured by a third qubit, which in turn is measured by another qubit, and so on and so on. If you have a large environment that you can entangle to lots of things, this can very quickly become a huge system of entangled um, um, uh, qubits, let's say, high dimensional systems. And in topology, this corresponds to this very nice structure of knots. This is just for you to visualize. They're all entangled together. However, if you remove one of them, the whole structure falls apart. No subset of these knots is entangled, only the whole thing. And so that's one nice metaphor, if you like, or a mathematical analogy of how classicality emerges out of full quantum dynamics. So all of these systems here on the left are basically entangled together. They cannot be described classically. You can violate Bell's inequalities with them. You can do all sorts of things. However, no subset, no two, no three of them are entangled. They really behave fully classically, much like the alpha particle that ultimately appears to go in a straight line. This is exactly the same. Every subset behaves logically, classically. It's either in a state 0 or a state 1, but the whole thing is in a state that we call a GXS, maximally entangled, highly entangled state where all zeros and all ones exist simultaneously. So this slide is simply to explain that we perfectly understand how a classical world emerges. And the larger the object, as you can see, the more entanglement you are likely to have through just spontaneous natural interactions. And therefore, it means that it's going to be harder and harder on subsystems to confirm that they are genuinely quantum mechanical. So that's what explains to us really why quantum technologies and how to scale them is really a very difficult problem. And it's again because of entanglement, because there are entanglements that we like and we want to utilize, and there are other entanglements with the rest of the universe, which are also there, and they are very hard to shield from if you have a complex system. So now just a couple of things to mention, because I was asked to give maybe a few minutes for discussions, and this could be more interesting than maybe just me talking. But we went with this logic, trying to go beyond ordinary non-living matter and try to really produce entangled states between living systems, in this case, a very simple bacterium and light. So this was one of the experiments that my colleague, my postdoc at that time, Dave Coles, did in 2016, 17, I think, where he took a tiny cavity, two mirrors which are very close to one another, about a micron distance, put the bacterium inside, and then did some spectroscopy on this to observe what happens. And I don't want to bore you again with all of these things. But what was interesting, the final conclusion that's the paper if you want to read more about it. The final conclusion is that this experiment managed to create an entangled state between a living system. This bacterium was alive, room temperature experiment, between a living system and the light inside this cavity. And the signature of that is actually relatively simple in this case, which is to observe shifts in energy levels. When the bacterium is outside of the cavity, it has a certain energy level structure, which you can probe spectroscopically. You can shine some light and observe what comes out. When you put the bacterium in a cavity, because it forms an entangled state now, these energy levels shift. And you can actually observe the gap in these shifts, and that tells you even how entangled these systems are. And just to say that we can use the full techniques from quantum optics or from solid state physics, and we can even quantify how much the dipoles, if you think about the bacterium as made up of lots of dipoles that are capable of absorbing light and emitting light, and if you think of light as being just simply another quantum harmonic oscillator, then you can even plot how the entanglement changes as you bring the cavity mirrors closer to one another and on resonance, if you like, in that language, with the energy structure of the bacterium. So this to me was exciting because simply there are many views which suggest that when living systems encounter quantum effects, they will act in a way to collapse them. And one of the research directions that I'm interested in is to show that this is not correct. Actually, that there is no contradiction between being alive and being in a superposition of being in an entangled state. So I think this will be very exciting. No one has actually done this with two systems. No one has entangled two living quantum systems. That's really going in the direction of Schrödinger's cat, if you like, to show that anything can really exhibit this property. But I think this experiment would be simply hugely exciting because it would tell us a lot about whether quantum mechanics really holds up at that level, whether it makes sense to really think about these systems in a fully quantum way, which I'm advocating. The other more recent experiment, this is again just to tell you about two of these exciting experiments, was a tardigrade. So a colleague of mine in Singapore, Rainer Dumke, took a tardigrade, living tardigrade, coupled it to a superconducting qubit and observed some very similar behavior. In fact, observed even entanglement between superconducting qubits, but modulated by the tardigrade. And again, I don't want to bore you with the details of this. The upshot is what I'm showing you here, and that's something we'd like to do. I've been very lucky to be supported by two foundations back to back. The first 5 years was the Martin School, which funded most of the stuff I talked about in the last few slides. And now I have funding from the Moore Foundation. And the focus really is to scale up this experiment with one single bacterium, to have two bacteria confined to two cavities, microcavities that are separated by something that we could call a macroscopic distance, half a meter, whatever is feasible, experimentally speaking, and then to send a single photon in a superposition to get it absorbed by the two, which would then result in the creation of quantum entanglement. And that's what's interesting to us. And the second thing that's something I would like to really conclude with. So basically, this first direction is simply exploring to what degree can all quantum effects exist even in the biological domain. But to a physicist, I think the most exciting question, and this is maybe the biggest outstanding problem in physics at present, is whether gravity is also quantum mechanical. And this is just a brief proposal, which I think a number of groups are now trying to implement. So there is almost a race going on. I think that's very exciting that maybe within the next 5 to 10 years, we will know whether this is so or not, is to really entangle two massive objects through the gravitational interaction. So this will be performing a little bit like the control NOT gate, speaking in terms of information, but purely by using the quantum nature of the gravitational field. So Chiara Malletto and myself wrote the paper simultaneously. We coordinated it with Sugata Bose at University College London and published these two proposals. And like I said, this generated a lot of excitement because it seems to give us a way, by using this logic of entanglement, it gives us a way to show that even this last outstanding force, the fourth force, if you like, gravity, the fourth force that's the only one that's still classical in some sense. We have no evidence that's quantum. This would give us some inkling of whether we ought to quantize it or not. If it's capable of entangling masses in this way, then at least some degrees of freedom of gravity must be quantum mechanical. So that's hugely exciting. And ultimately, the picture, that's something I want to conclude with. The picture, you could ask, what does this mean? This is just this image of lots of people basically observing a sequence of outcomes, a bit like this sequence of controlled knots that I was showing you, but now applied to human observers. And I think frequently people say, what does this mean that all of these multiple realities really exist as quantum waves? I think that there is a very interesting view that's related to this, which even suggests that at the level of the universe, you could think of time itself as being another quantum branch. So even time, not just other things that I was saying emerged through entanglement, but this view would say that at the level of the whole universe, even different instances of time could be thought of as some kind of entanglement between different bits of the universe. The slide here says, because frequently when you talk about all of these possibilities existing, but we are just in one of the branches, people frequently say, what does it mean to be in another? How does it feel? What does it feel like to be in another branch? And I think the simplest way to understand that, if this picture is correct, is basically to say, what does it feel like to wait for 10 minutes and ask exactly the same question? And it's an interesting view, because it's a view according to which the whole universe could be thought of as being static in a quantum state that doesn't even change in time. It's an eigenstate, if you like, of the Hamiltonian of the universe, if that even makes any sense. However, the time emerges in a relational, in a relative way. This is a view advocated a while back by Page and Wouters. So basically, there is a hugely entangled state between all of the matter, all of the fields, all of the Q numbers that I was describing on the one hand, and the space structure without the time, the space structure of the universe, the geometry, the spatial geometry of the universe. And this hugely entangled state, one state of matter and fields corresponds to one spatial geometry plus another state, another spatial geometry, hugely entangled state, is something that then ultimately could give rise to temporal evolution. So even time in this way could be understood as a consequence of quantum entanglement. So these to me are very, very interesting views and interesting questions to even ask ourselves. How would one test this kind of view? Could you really violate Bell's inequalities? Could you be talking about different superpositions of times in the same way that we talk about the superpositions of spatial positions and things like that? And so let me conclude here, because I think I'm coming to the end of the presentation. The main question really is quantum physics applicable to all objects at all scales, micro and macro, and the whole universe? And if we push the boundaries in this way, it is possible that we will discover that this is not the case. But my intuition is that it's not going to bring us back to classical physics. It's not going to be a collapse. It's going to be another theory that's even more general than quantum mechanics. I think, to me, it's more likely, from what we understood historically, how science evolved, that we're going to find an even more general theory, for which quantum mechanics is a special case, in the same way that classical physics, as I was saying, is a very special, exponentially small case of quantum mechanics. The reason why I like, spiritually speaking now, the reason why I like this view of the universe is because everything is made up of the same thing. There are no particles and waves, and whether something is a particle or a wave depends on how you measure it, which is what Copenhagen would say. Everything simply is a quantum wave. And the reality, the classical reality, approximately, what we see approximately as classical reality, is really just one special branch of a much larger quantum reality that emerges from coupling between different quantum waves. Which is exactly, I'm more or less reciting, I think, what Schrödinger had in mind when he was talking about these things. Time can be incorporated in this. That's the last thing that I mentioned. But I think the real exciting experiments to be to be basically aware of and to be looking out for are the ones which are pushing these quantum effects into chemistry, biology, and really testing whether, first of all, whether they hold up in that domain. Secondly, in biology, whether they're even used by biological systems. There are very exciting ideas that in quantum biology, basically, living systems could, in fact, have even evolved to do some small-scale quantum computations. And then, like I said, we might even get an answer whether some gravitational degrees of freedom are really quantum mechanical. And this will give us a lot of information how to proceed, because at the moment we really don't know what to do in that direction. I will stop here. Thank you very much for your attention, and I'm happy to answer any questions if there are any. Thank you.
Hello. Am I audible to you?
Just to say that you're breaking up, I can't really hear properly what the question is.
Professor, am I audible to you?
You are now. That's great for the first time.
Yeah. So I'll be passing on to the audience, amongst the audience who have some questions.
Perfect. Okay. Please do. Yeah, perfect. I can hear you perfectly now. Great.
Thank you, Professor. That was a very wonderful talk.
Thank you.
Quite revolutionary proposal.
Thank you.
If Newton laws are result of quantum entanglement, are there attempts to deduce quantum Newton's equations, laws of motion, from quantum equations? Is number one question. Number two, are there attempts to experimentally verify it?
Excellent. Yeah, both questions are excellent questions. That's possibly also the first question is maybe would be clearer if we learned quantum mechanics maybe the way it was originally formulated by Heisenberg, which is to say that he was very keen to maintain the classical limit. So the answer is yes, you can do that. And in fact, some approaches to quantum mechanics are, like Heisenberg's, are taking the classical laws as still being correct. So the way Heisenberg would put it is, he would say, I'm not changing dynamics. I'm still assuming Hamiltonian dynamics. But the entities that obey Hamilton's equations of motion are these Q numbers now. So that was his big discovery. That instead of thinking of the position and the momentum as just real numbers, he said if you think of them as these Q numbers that have specific algebraic properties that they cannot be specified simultaneously, they don't commute and things like that, then you don't need to do anything with classical dynamics. You don't need to modify classical dynamics at all. And I think that's now directly linked with your second question as well. You're absolutely right. You can measure the deviations. So if you say this particle now ought to travel perfectly in a straight line according to Newton, what various diffraction experiments are really teaching us ultimately is that there is a deviation to this. They don't go in straight lines. In fact, if you have two particles that would classically have the same speed and go in the same direction, their trajectories would remain parallel. just like in Euclid, two parallel lines, they would never meet. However, in quantum mechanics, and that's what you can test, if you have two quantum particles, if you like, emitted, like the alpha particles, then they're even if they start, even if you can prepare them with really well-defined velocities, you could actually test that ultimately these two lines would not stay parallel, and there would be a possibility to detect them in the same spot. And this would tell you exactly the deviation with respect to Newtonian behavior. So these are very good points. And yes, we can test them and we can quantify.
So we have a few more queries. I'll pass on the
Of course,
mic
please do.
to our audience.
Hello, am I audible?
Yes.
Okay. So, hello, sir. My name is Manali.
Hi.
I'm from IIT Bombay. And actually,
Hi.
I'm working on magnetometry. I have two queries. First query is while you were discussing about the classicality arises because of entanglement. There you were saying that all the particles are entangled and all the states emerge in a superposition. But my point is that entanglement is a monogamy process. Now, how are you maximally entangling all the systems?
Excellent point. Actually, that's the key to what I was saying. I didn't mention the word monogamy, but it's so nice that you brought it up. That's precisely the point. The point. One way of understanding why only all of the systems can be entangled, but no subsets. It is because of monogamy. So if you think about two particles as take any two particles out of these many particles, because they are entangled maximally to the rest of the particles, two of them cannot be entangled as well. So that's a very nice way of explaining that it's monogamy that prevents all of the other entanglements, other than at the highest level. So at the highest level, you have a state where all of them, let's say, are in the state 0, plus all of them are in the state 1, a GZ state. But what this implies is at the lower level, nothing is entangled at all. And so this is something you get for free, if you like, from unitary quantum dynamics, which is why I'm saying you don't need to postulate any special measurements on top of it. You already get classicality out of this. Exactly. So it's the monogamy that prevents this.
Okay, so I have one more question. So the other question is while you were talking about the tardigate, so you were saying that you are having two cavities. So my question is, can we entangle two of the cavity systems together?
Yes, we have excellent point as well. We have done this with, let's say, simple atoms. You can confine atoms in separate traps that are separated by, let's say, 1 meter. And then you can observe, you can excite them both. That's one way of doing. That's what some people have done that. You can excite them both, then observe a single photon emitted. And if you make sure that you don't know which of the two systems has emitted that single photon, then effectively what this does is creates an entangled state between the two atoms. So one atom is excited, the other one is ground, plus quantum mechanically vice versa, the other way around. So basically, people have entangled much simpler objects using this kind of technique, having two different traps or two different cavities and two atoms in each, one in each. But what we are trying to do is to achieve the same with a living system. And that's much more complicated because making sure that these living systems are identical and emit, for all practical purposes, identical light, if you like, that they should be as indistinguishable as possible, is extremely difficult to achieve in an experiment. But the good thing, like I said, is that it's already been done with quantum dots, with atoms. We know we can do it. The question is really, can you do this with living systems? And to me, that sounds really spectacular. You know, it's going in the direction of Schrodinger's cat. And of course, confirming that they're entangled could be equally difficult. How do I measure then afterwards to really convince you that these two are in an entangled state? So there are many difficulties with these experiments.
Hello.
Hi.
Thank you, Professor. This is Sanjay from IIT BHU.
Hi. Hi, Sanjay.
Actually, you are saying that the observer is a physical system, okay? And at the same time, you are saying that the measurement as a process of transformation is just a type of creation creation of entanglement
That's it.
between system and observer.
That's it.
Here, my question is, who projects the entanglement?
Excellent. You are absolutely right that you need to assume that certain things are just given to you. So entanglement in my picture is simply something that happens spontaneously through natural dynamics. So I'm not trying to explain that. I'm simply assuming the usual laws of quantum mechanics. And I'm assuming what would happen if I describe the whole process quantum mechanically, where, for instance, an atom emits a photon, the photon gets absorbed by the detector produces the current, it gets displayed on the computer screen, and then I look at it. So basically there is light shining, enters my eye, and the whole thing. And I'm thinking of the whole, every instance, every step of this interaction, I'm thinking as quantum waves coupling to one another. But I'm not explaining, I'm simply take that as a given. And what I'm saying is that you don't need any extra postulate. You don't need to now assume that when I see one outcome, there are no other outcomes and things like that. I think all of this already captures the measurement. But the beautiful thing, I mean, this is of course just a hypothesis. We haven't really tested this properly with macroscopic objects, so I don't really know whether our consciousness works this way. Maybe it doesn't. That's what's interesting. But if it really is like this, then entanglement tells you that the situation is completely symmetric. So the same way that I'm observing an atom which emits a photon, you could say that the atom, by the virtue of being entangled to me, is also observing me. So for every relevant information state of the atom, there is the corresponding relevant state in my Q numbers that corresponds to that state of the atom. It's perfectly symmetric because entanglement, atom is as entangled to me as I'm entangled to the atom. It cannot be any different. It must be the same degree of entanglement. So this is very interesting because I think favoring us, for instance, or complex systems, and thinking of us as observers is making us misunderstand quantum mechanics and not really apply it properly to the macroscopic domain. I think we should be thinking of any systems capable of interaction as also capable of observing other systems. And to me, it sounds very nice and unifying. There's no more any distinction between the two. But I'm assuming unitary quantum dynamics. That's correct.